If you've ever searched this question online, you've probably seen one of those slick little calculators that spits out a clean number. Type in Mars, get an answer in months. Type in Neptune, get an answer in years. Simple, tidy, satisfying, and almost completely misleading. Because here's the truth nobody puts on the label of those calculators. There is no single travel time to any planet in our solar system. Not one. The real answer depends on where that planet happens to be in its orbit the day you launch, how much fuel you're willing to burn, whether you're going for speed or for a controlled arrival, and whether you're willing to let the gravity of other planets bend your path along the way. Two real spacecraft can launch toward the exact same planet and arrive years apart, using completely different strategies, and both of them would be telling you the truth about how long it took to get there. So instead of giving you a fake, oversimplified number, I'm going to walk you through what actual spacecraft, built by actual space agencies, have actually measured mission by mission, all the way from the innermost planet to the edge of what we've ever managed to reach. Real missions, real years, real reasons why some of these numbers are going to surprise you. Before we get into the real mission by mission numbers, it's worth understanding exactly how those oversimplified calculators arrive at their misleadingly clean answers, because seeing the shortcut makes the real complexity click into place. Most of them take the average distance between Earth and a planet, divide it by some fixed spacecraft speed, usually borrowed from a single pass mission, and call it a day. That's roughly the same as calculating how long it takes to drive from your house to a friend's across town by dividing the straight line distance by your car's top speed, ignoring the roads, the traffic lights, the fact that you can't actually drive in a perfectly straight line through people's backyards. Real interplanetary trajectories are curved deliberately, and the curve itself, along with the planet's actual positions on launch day, does most of the work in determining how long the trip really takes. Let's start with the most counterintuitive one in the entire solar system, because it breaks almost everyone's intuition immediately. Mercury. It is the closest planet to the Sun. It's also, by a wide margin, one of the hardest planets to actually reach and settle into orbit around. And understanding why tells you almost everything you need to know about how real interplanetary travel actually works. Here's the problem. When you launch from Earth, you're not just falling toward the Sun, you're carrying all of Earth's own orbital speed with you, roughly 30 kilometers per second, sideways around the Sun. To reach Mercury, you don't just need to travel inward, you need to shed an enormous amount of that sideways speed, because the deeper into the Sun's gravity you go, the faster everything naturally moves, and Mercury itself is already screaming around the Sun at nearly 48 kilometers per second. Slamming on the brakes that hard, using only rocket fuel, would require an almost impossible amount of propellant. So instead, spacecraft heading to Mercury do something that sounds almost backwards. They use multiple flybys of other planets specifically to bleed off speed, gravitationally, for free, a little at a time. The first mission to ever fly past Mercury, NASA's Mariner 10, launched in November 1973 and reached the planet in about 147 days, under 5 months, but it was only ever designed for a flyby, a quick pass, not orbit insertion, so it never had to solve the harder problem of actually slowing down enough to stay. The first spacecraft to actually enter orbit around Mercury was NASA's MESSENGER, launched in August 2004. Its journey took 6.5 years, involving 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself, each one carefully bleeding off just enough speed to make the next step possible before it finally settled into orbit in March 2011. And right now, as you're watching this, there's a spacecraft still making that exact same trip. The joint European and Japanese mission Bepi Colombo launched in October 2018, and its full journey to Mercury requires 9 separate planetary flybys, 1 of Earth, 2 of Venus, and 6 of Mercury itself, spread out across roughly 8 years of cruising before it can finally settle into orbit. The mission actually hit a real complication along the way. In 2024, engineers discovered a power glitch in the spacecraft's electric propulsion system that reduced its available thrust, and rather than risk the mission, ESA's flight dynamics team redesigned the remaining trajectory around the lower available power, pushing the planned orbit insertion date from December 2025 to November 2026. Bepi Colombo completed its 9th and final flyby back in January of this year and is now, right now, in its final approach, on track to finally enter orbit around Mercury this coming November, a genuine 8-year journey to reach the planet that's actually the closest one to Earth for a meaningful chunk of every year. That's the paradox at the heart of interplanetary travel. Proximity on a map means almost nothing. Orbital mechanics is what actually decides how long a trip takes. Venus tells a very different story, mostly because it doesn't require nearly as much of that delicate braking. The very first spacecraft to ever successfully reach another planet at all was NASA's Mariner 2. launched in August 1962, which flew past Venus in about 109 days, a little under 4 months, and confirmed for the first time in human history that Venus's surface was a genuine inferno rather than the tropical paradise some scientists had still been hoping for. Later missions took different amounts of time depending on their goals. NASA's Magellan mission, designed to map Venus's surface using radar through its thick clouds, launched in May 1989 and took a slower, more fuel-efficient route, arriving after about 15 months because Magellan wasn't in a hurry. It was optimizing for the amount of fuel it would have left over for its actual science mission once it got there. That's a pattern you're going to see over and over in this video. Speed and efficiency are almost always a trade-off, and mission planners choose deliberately based on what the spacecraft actually needs to do once it arrives. Then there's Mars, the planet everyone actually wants a number for, because it's the one most seriously being discussed for an eventual human mission. Using what's called a Hohmann transfer orbit, essentially the most fuel-efficient curved path between two orbits, a spacecraft launched during the right window, which opens roughly once every 26 months, when Earth and Mars line up favorably, takes somewhere between 6 and 9 months to arrive. NASA's Perseverance rover, launched in July 2020, is a good recent real-world example. It landed on Mars in February 2021, a journey of about 7 months, 203 days, almost exactly in the middle of that typical range. The exact number shifts mission to mission, depending on the specific launch date within that window, the spacecraft's mass, and how much fuel is available for course corrections along the way. It's worth pausing here on a detail that trips a lot of people up. The distance between Earth and Mars isn't fixed. Because both planets are moving around the Sun at different speeds on different sized orbits, the actual gap between them swings wildly, from as close as about 33 million miles at their nearest approach to as far as roughly 250 million miles when they're on opposite sides of the Sun. You can't just launch toward Mars whenever you feel like it and expect a consistent trip. Miss the launch window and you're either waiting another 26 months for the next one, or burning vastly more fuel to fight against orbital mechanics that aren't cooperating with you. Before we leave the inner solar system behind, it's worth pausing on the region that sits between Mars and Jupiter because it complicates the picture of what a planet-to-planet trip even means. The asteroid belt isn't a wall of rubble the way movies sometimes portray it. It's a vast, mostly empty region containing millions of small bodies spread across an enormous volume of space, and spacecraft pass through it routinely with essentially no risk of collision. NASA's Dawn mission, launched in September 2007, actually made the belt itself the destination, using efficient ion propulsion to first reach the giant asteroid Vesta in 2011, then depart Vesta and travel onto the dwarf planet Ceres, arriving in 2015, becoming the first spacecraft in history to orbit 2 separate deep space bodies on a single mission. That kind of multi-stop itinerary simply isn't possible with a traditional chemical rocket, because there's no fuel margin left over for a second major maneuver after the first arrival. It took Dawn's gentle, continuous ion thrust, the same category of engine now flying on Bepi Colombo, to make a 2-stop tour of the solar system's interior actually feasible. Now we cross the asteroid belt and head into the outer solar system, and this is where travel times stop being measured in months and start being measured in years, sometimes many of them. Jupiter is the first major test of that. NASA's Pioneer 10, launched in March 1972, was the first spacecraft to ever cross the asteroid belt and reach Jupiter, arriving in December 1973, a journey of about 21 months, under 2 years, on a fast, direct trajectory. But direct and fast isn't always the plan. NASA's Galileo mission, launched in October 1989, actually took nearly 6 years to reach Jupiter, dramatically longer than Pioneer, and that wasn't a mistake, it was a forced redesign. Galileo was originally supposed to launch on a more direct, faster trajectory using a powerful upper stage rocket. But after the Space Shuttle Challenger disaster in 1986 grounded that rocket for safety reasons, engineers had to completely replan Galileo's route using a much less powerful booster, which meant looping the spacecraft through multiple gravity-assist flybys of Venus and Earth, twice, just to build up enough speed the hard way, adding years to the trip. NASA's Juno mission, launched in August 2011, took about 5 years to reach Jupiter, using one Earth flyby along the way for a gravity boost. And New Horizons, which we'll talk about more in a moment, blew past all of them, reaching Jupiter in just 13 months after its 2006 launch, because unlike every other Jupiter mission before it, New Horizons was launched directly on the most powerful rocket configuration NASA had ever used for a planetary mission, specifically because its real destination was so much farther away that every year saved early in the trip actually mattered. Saturn stretches things out even further. NASA's Pioneer 11 took about 6.5 years to arrive after launching in April 1973. NASA's Cassini mission, launched in October 1997, took a genuinely epic 7-year journey, using gravity-assist flybys of Venus twice, then Earth, then Jupiter, essentially using the entire inner solar system as a slingshot before finally arriving at Saturn in 2004, where it would go on to spend the next 13 years actually studying the planet and its moons up close. A mission so successful that its final deliberate plunge into Saturn's atmosphere in September 2017 became one of the most emotional moments in the history of planetary science, precisely because of how long and how much had been invested to get it there in the first place. Beyond Saturn, human spacecraft have visited Uranus and Neptune exactly once each, ever, and both visits came from the same mission. NASA's Voyager 2, launched in August 1977, reached Uranus in January 1986, a journey of about 8.5 years, and kept going, reaching Neptune in August 1989, roughly 12 years after its original launch. To this day, Voyager 2 remains the only spacecraft to have ever flown past either of those two planets. No mission has been sent back since. Everything we know, in detailed up-close imagery about Uranus and Neptune, comes from data collected during those single flybys decades ago, from a spacecraft that's now so far from Earth, it's actually left the sun's direct influence entirely and is drifting through interstellar space. It's worth sitting with just how remarkable that timing actually was, because it wasn't purely luck. Voyager 2's entire trajectory was designed to take advantage of a rare planetary alignment, one that happens roughly once every 175 years, where Jupiter, Saturn, Uranus, and Neptune all sit positioned closely enough along the spacecraft's path that a single mission could use each planet's gravity to slingshot toward the next, saving years of travel time and enormous amounts of fuel that would otherwise have been required to reach each successive world on its own. Mission planners in the 1960s and 1970s recognized that alignment was coming and built the entire Voyager program specifically to exploit it. Miss that particular window, and a mission attempting the same multi-planet tour today would need a completely different, almost certainly far longer trajectory, because the planets simply aren't going to line up that conveniently again for another century and a half. And then there's the journey that, for a long time, held the record for the longest deliberate planetary trip in human history. New Horizons, launched in January 2006, took 9.5 years to reach Pluto, arriving in July 2015. It remains the fastest spacecraft ever launched directly from Earth, and it still took nearly a decade to get there, which tells you everything about just how vast the outer solar system actually is. Pluto isn't even counted as a full planet anymore by the official definition adopted in 2006, but New Horizons remains the only mission to have ever given humanity a close, detailed look at it. And that one journey alone, at the fastest speed humanity has ever managed for a direct planetary launch, still took the better part of 10 years just to get there, let alone actually study it once it arrived. So why does the exact same trip to the exact same kind of destination sometimes take twice as long or more depending on the mission? This is genuinely the most important thing to understand if you actually want the real answer to this question, instead of a single misleading number. It comes down to a handful of variables that mission planners are constantly trading off against each other. The first is simply how much fuel a rocket can afford to burn. A completely direct, straight-line style trajectory would technically be faster in theory, but it demands an enormous amount of propellant that has weight, and weight that has to be launched, which multiplies the size and cost of the rocket needed to get off Earth's surface in the first place. That's why most missions instead use what's called a Hohmann transfer, an elegant, curved minimum energy path that uses far less fuel by letting the spacecraft essentially coast along an efficient orbital arc between planets rather than fighting orbital mechanics head-on the whole way. The second, and arguably the cleverest tool in the entire toolkit, is the gravity assist, sometimes called a slingshot maneuver. By carefully flying close to a planet on the way to your real destination, a spacecraft can actually steal a small amount of that planet's own orbital momentum, speeding up or slowing down and bending its trajectory entirely for free without burning a drop of fuel. This is exactly how Cassini used Venus again, Earth, and then Jupiter, to build up enough speed to reach Saturn without carrying an impossibly large amount of propellant. It's why Galileo's trip to Jupiter ballooned from a potential direct shot into a 6-year journey once its original rocket became unavailable. The trade-off is time. Gravity assists are close to free in terms of fuel, but they cost you patience, sometimes years of it, because you have to wait for the planets involved to actually be lined up correctly for the flyby to work in the first place. The third variable is simply what the mission is actually trying to accomplish once it arrives. A flyby mission, like Mariner 10's pass of Mercury or New Horizons' pass of Pluto, doesn't need to slow down much at all when it gets there. It just needs to be pointed correctly and moving fast enough to capture data as it zooms past. An orbiter mission, like Messenger at Mercury or Cassini at Saturn, has to do the much harder job of actually shedding enough speed to be captured by the target planet's gravity and settle into a stable orbit, which almost always adds significant time and complexity to the trip. Because you can't just show up moving fast, you have to arrive moving at exactly the right, much slower, speed. Now, all of these numbers we've walked through use what's currently considered conventional propulsion, essentially chemical rockets and careful orbital mechanics, the same basic toolkit humanity has been using since the start of the space age. But it's worth being honest about where propulsion technology stands right now and where it's actually headed, because this is where a lot of the more exciting, forward-looking numbers come from, and where it's important to separate real, funded research from pure speculation. Ion propulsion is real flying technology, not science fiction. NASA's Dawn spacecraft, launched in 2007, used ion engines to visit both the asteroid Vesta and the dwarf planet Ceres, the first mission ever to orbit two separate deep space destinations, precisely because ion engines, while producing very gentle thrust, can run continuously for months or even years at a time, gradually building up enormous total speed changes that a short, powerful chemical rocket burn simply can't match over the long run. Bepi Colombo, the very Mercury mission we started this video with, is using exactly this kind of solar electric propulsion for its multi-year cruise, which is part of why the timeline of that particular mission has so much built-in flexibility, and also part of why the recent thrust reduction was able to be worked around with a revised trajectory rather than ending the mission outright. Looking further ahead, NASA and other space agencies have real active research programs into nuclear thermal propulsion, engines that would use a nuclear reactor to superheat propellant and produce significantly more thrust efficiency than today's chemical rockets, potentially cutting a crewed trip to Mars down from 6 or 7 months to something closer to 3 or 4. NASA and DARPA have been jointly developing a demonstration program for exactly this kind of engine in recent years, aiming for an actual in-space technology test, though as of now it remains a demonstration and testing effort, not something flying operational missions to other planets yet. And then there's the genuinely fastest human-made object ever built, which is worth mentioning because it puts everything else in this video into perspective. NASA's Parker Solar Probe, which has been diving repeatedly closer and closer to the Sun using a series of Venus gravity assists, reached a top speed of roughly 692,000 kilometers per hour during its closest solar passes, faster than any spacecraft in history, by a wide margin. Parker isn't going to a planet. Its mission is studying the Sun's outer atmosphere directly, but the sheer speed it's achieved shows you that the ceiling on what's technically possible is far higher than any of the mission profiles we've walked through today. The reason no planetary mission has been built to actually fly that fast toward a destination is entirely about the specific mission goals, the available propulsion budget, and honestly, current cost constraints, not some hard physical limit we haven't figured out how to push past yet. It's also worth being clear-eyed about crewed missions specifically, since a robotic spacecraft and a mission carrying astronauts don't necessarily follow the same math. NASA's Artemis program is currently focused on returning astronauts to the moon as a stepping stone, with a crewed Mars mission still in the long-term planning stages rather than an active flight schedule. Private efforts are also part of this picture. SpaceX has stated ambitions for its Starship vehicle to eventually carry crews to Mars using a standard Hohmann-style transfer, targeting a journey in the same rough 6 to 7 month range as robotic missions like Perseverance, though as of now Starship has not yet flown an actual Mars transit, and any timeline for a crewed flight remains a target rather than a confirmed schedule. The honest distinction to hold on to here is the same one that's run through this entire video. A number like 6 months to Mars describes a specific, physically grounded trajectory using known propulsion, not a promise about when any particular mission, robotic or crewed, will actually fly it. So if someone asks you the real answer to how long it takes to reach each planet, here's what an honest mission-by-mission answer actually looks like, using real spacecraft that have actually made these trips. Mercury, using gravity assist orbiters like MESSENGER and Bepi Colombo, takes somewhere between 6.5 and 8 years. Venus, depending on the mission's goals, takes anywhere from about 4 months for a fast flyby to over a year for a more fuel-conscious orbiter. Mars, using a standard efficient transfer orbit, takes roughly 6 to 9 months. Jupiter ranges enormously, from as little as 13 months on New Horizons' direct trajectory to nearly 6 years on Galileo's forced flyby-heavy reroute. Saturn has taken anywhere from about 6.5 to 7 years on the missions that have actually reached it. Uranus and Neptune, based on the only mission that's ever gone there, Voyager 2, took 8.5 and 12 years respectively. And Pluto, using the single fastest direct planetary trajectory ever launched from Earth, still took 9.5 years. There is no single correct number for any of these planets. Every single one of those figures is real, measured, and came from an actual spacecraft that actually made the journey. And every single one of them would have been different if the mission planners had made different choices about fuel, speed, gravity assists, or what the spacecraft needed to accomplish once it got there. That's not a flaw in the question. That's the actual, honest, complicated answer. And it's a far more interesting one than any calculator spitting out a single clean number could ever give you. What's coming next is genuinely worth watching for. Bepi Colombo is due to finally enter orbit around Mercury this November, closing out an 8-year journey that started back in 2018. NASA's continuing work on nuclear thermal propulsion could, within the coming years, actually demonstrate a real flight-tested engine capable of cutting the Mars transit time by a third or more. And every time a new mission gets announced to any of these worlds, the specific number you'll hear reported is going to depend, once again, on exactly the same handful of variables we just walked through. How much fuel is available, whether the planets happen to be lined up favorably, whether the mission is designed for a quick flyby or a long-term orbit, and how much patience the people running it are willing to trade for how much fuel they're willing to burn. That's the real story behind these numbers. Not a simple countdown clock ticking down to arrival, but a genuine engineering puzzle, solved a little differently every single time, by real scientists making real trade-offs for every single mission humanity has ever sent beyond our own planet. And it's a puzzle that's still actively being solved. Every one of the missions we've walked through today, from Mariner 10's 5-month dash past Mercury in 1973 to Bepi Colombo's careful 8-year approach happening right now, represents a different answer to the exact same underlying question. Given the fuel we have, the rocket we can build, and the planet's actual positions on the calendar, what's the smartest possible way to get there? There isn't a single correct strategy, because the right answer changes depending on what the mission is actually trying to accomplish once it arrives, and that's precisely why the same trip has been made a dozen different ways, in a dozen different amounts of time, across the history of spaceflight. If you want to keep track of Bepi Colombo as it finally reaches Mercury orbit this November, or catch the next major mission announcement to any of these worlds, subscribe, because there's almost always something new in motion somewhere in the solar system. Drop a comment with which of these missions surprised you the most, whether it's Galileo's 6-year detour, Voyager 2 still being the only spacecraft to ever visit 2 entire planets, or New Horizons somehow still taking nearly a decade, even at the fastest launch speed ever achieved. And share this with anyone who's ever been handed one of those oversimplified travel time calculators and told it was the whole answer. Because it never was. The real answer was always more interesting than the number.